the typical narrative of an introduction, but I think those are the reasons Stefanie is here, is one to watch, and I'm really excited about her talk.
Awesome. My slides come. Okay. Thank you very much, Sonia. So my talk is called Learning Models of Language, Action, and Perception for Human-Robot Collaboration. Just get my stopwatch there. And we're at a really exciting time in robotics today. Sonia already mentioned some work I was fortunate to take part in at MIT with an autonomous forklift that could drive around warehouse environments and manipulate pallets. And we just had the huge news from Waymo just last week that they're starting unmanned self-driving testing in sunny Arizona, which Waymo is so conservative that I really feel like this is like the high technical risk parts are done, and we're going to have self-driving out there in sunny places anyway very soon. And it's going to change everything. We have drones everywhere. This is the drone for my robotics class at Brown. It's a Raspberry Pi Python autonomous drone. Each student gets their own drone, and it can autonomously fly around in indoor environments. This is our demo day where everybody was flying their drones. And we were fortunate to have Skydio come. They're a company out here in the Bay Area. They have an autonomous vision-based drone with 13 cameras, 2 stereo pairs for each side of the cube, plus a high-res color camera, and it was flying autonomously through trees and not hitting stuff. So a really amazing amount of accessibility and autonomy in this area. And we have this long-term vision towards robots in our homes, in our lives, taking care of our kids. This is my son when he was a baby. Sonia mentioned changing diapers, and I heard Rod mention this morning the sort of grain population. They're going to take care of our parents maybe, or maybe even us. And so as this vision becomes a reality, one of the most important problems to address is how are we going to interact with these robots and, going beyond interaction, collaborate with these robots on highly complex tasks with highly capable, collaborative, and autonomous robots. So the sort of standard approach is some kind of device that you use to interact with the robots. So with the PR2, it's like a PlayStation controller or the PackBot. With the forklift, it was a tablet. With the Waymo devices, there's a screen in the back seat. Instead, what I envision is a world where you interact with the robot as if it was another person. And to do that, you use the modalities you use with other people, language and gesture and conversation and physical actions in order to collaborate with the robot on complex tasks. So for example, for the forklift, you might imagine that you'd say something to it like, put the metal crate on the truck. And then the robot hears those words and somehow has to map between words like metal crate and something that's out there in the environment that it needs to get its tines through and lift up and move it to some other place in the environment that's sort of specified by these words of the truck. And so it has to map between this sort of crisp symbolic language and the noisy, messy world as perceived through its sensors, and somehow convert this to electrical signals to its motor at the end of the day. And this is challenging for a lot of reasons. One is this mapping problem is really hard. A second reason is that people don't like to stick to a fixed vocabulary and grammar when they're talking to anybody, much less a robot. So, for example, we did a data collection quite a while ago now where we showed annotators a video of the robot doing something. This is the video. It lifts up the pallet, drives forward, puts it down on the truck, and it's just going to restart now. And we said, give us a natural language command that you would use to command an expert human operator to carry out the action that you see in this video. And somebody said, put the tire pallet on the trailer. Another person said, place the pallet of tires on the left side of the trailer. So you kind of get these sort of what we expected kinds of commands that tell what the robot's doing. Another person gave much finer grained instructions. So they said, lift tire pallet, move to unoccupied location on truck, lower tire pallet, reverse to starting location, lower forks, end. And you'd like to be able to understand this too. You know, it's describing things in a slightly different way, but like there's totally scenarios where this sort of thing is is something you'd like to say to the robot and have it understand. And then if we kind of look at just a sample of some of the other commands we got from this video, no two commands are the same. Even though this video is sort of short, sweet, and simple, people really come up with a lot of diversity, and there's also subtle variations in the meanings of what they're describing. So some people abstract things away that other people kind of spell out. And we really want a robotic system to be robust to all of this variation. So pushing on this even more, you can sort of imagine you'd like to say to a forklift, put the metal crate on the truck, or to a home manipulator robot, get me a glass of water. But you might also want to give much finer-grained commands to that robot. So you might say to the forklift, move backwards 10 feet, because I'm going to pull my truck in front of you. Or you might say to a manipulator robot at home, go in the corner and just wait, because I want you out of the way for now. Similarly, you might also want to give much higher granularity commands. So I might say to the forklift something like, move everything from receiving to storage, and then I'm going to go away and come back an hour later, and the world has changed. It's now different. The robot has done its thing for an hour, and it's different. Or I might want to say to that home robot, clean my house, and then I go to work, and I come home, and my house is clean. So I'd like to be able to use language to specify any action that that robot is capable of. Very fine-grained actions and also very large, big, autonomous actions. And that means the language understanding module somehow has to hook into anything that that robot can do. Finally, we need to expect that our robots are not going to work all the time. It's sad, but it's true. And so in order to engage in an effective collaboration with a person, we can't just stop at the first failure, because in an extended interaction, no matter how good you are, you're going to encounter failure over days, weeks, months, and years. And so what we'd like the robot to be able to do is explicitly reason about mechanisms for detecting and then recovering from these sorts of failures. So for example, if you said to the robot, put the metal crate on the truck, and it didn't know where the truck was in the warehouse, or maybe there were two trucks in the warehouse, you'd like it to be able to take information gathering actions like which truck, ask a question, and then the person answers by maybe language or maybe gesture, and using the information from its answer, you'd like it to be able to go off and continue operating autonomously. So to sum all of this up, the problem that we need to solve if we want a language-using collaborative robot is that people want to talk to robots about everything they can see and everything they can do. And so our language model, our communication module, needs to connect to everything the robot can see and everything the robot can do if we really want a capable robot that can understand everything the person is going to say. So this is the problem that I'm trying to address through my research program, and I'll tell you about some of the steps in this talk. So the way that I think about this is I'm trying to enable human-robot collaboration by learning decision theoretic models for communication, action, and perception. So we need to have models for all three, communication, action, and perception, because people want to talk to the robot about everything it can see, that's perception, and everything it can do, that's action. The decision theoretic bit is going to allow us to reason about the robot's own uncertainty and detect and recover from failure. And the learning bit is going to allow us to scale to very large problems by leveraging large data sets. So by combining these two capabilities, we can then imagine sort of improving from experience, because if you can learn and you can detect and recover from failure, you can create labeled training examples for yourself and sort of get better over time. So what I'm going to do now is kind of define the formal mathematical framework I'm using to think about this. So you sort of imagine there's a robot in the environment, there's some objects out there in the world, and there's some kind of control system. And what we're all trying to do is figure out what goes on inside of that control system. And we get as input perceptual data, images from your camera, range sensor information from a LiDAR, and we're outputting actions, electrical signals from the motor to the motors at the finest grained level, but maybe we've learned some more abstract skills that we can then exercise. And the question is, what goes on inside that control system? So the approach that I'm taking is, and we also want to augment this with human input, so human language, like go to the truck, and communicative output, like having it be able to ask a question like which truck. So the approach that I'm taking for what goes on inside here is a model-based approach. So you get some observations. Using those observations, you create a model of what you think is going on out there in the world, and then you go off and try to pick actions. And the reason that we need the world model is because the language could hook into anything the robot can see. So we need some kind of model of what we think is out there in the world. So specifically, what I'm going to do is try to define a partially observable Markov decision process, or a POMDP. So POMDPs, I'll just go over them briefly. They're states. Each state is dependent only on the previous state. At each state, I get an observation. And the observation only depends on the current state. The shaded bit means I get to observe the observation value. The unshaded bit means that it's hidden. I can try to estimate it. So far, this is like an HMM, where I get the observations and try to estimate the hidden state. But I'm a robot, so I have actions. I get to choose an action at each time step. And depending on the action I choose, it causes the state to change in particular ways. And then I need a way of defining what good actions are, and that's done with a reward function. So at each state, I get a reward. And the goal of a POMDP, or solving a POMDP, is finding a policy, an action for each state that maximizes my expected discounted reward. So POMDPs in 20 seconds. So the problem with POMDPs is, unfortunately, they're undecidable. And when you tell somebody that you're working on POMDPs, they get worried because they're really hard and they're computationally intractable. And all of that is true. So when I say I'm using POMDPs, I think of that as the same kind of statement as saying that I'm using Python to make my robot do something. Python is also undecidable in general. I have told you something about what I'm doing and the way that I'm thinking about this problem. And I think it's pretty clear that a robot is a POMDP. But I haven't told you very much, the same thing as saying I'm using Python. The real question is, like, what data structures did I use, and how did I put everything together, and what algorithms are there? So in a graphical modeling framework, the question is, what are the random variables, and what are the conditional independence assumptions in order to enable efficient learning and inference in this general framework? So what I'm working towards is something that I call the human-robot collaborative POMDP, which is a specific POMDP designed to enable human-robot collaboration, to enable these capabilities. And I'll tell you right now, this is aspirational, right? So I'm going to tell you about the steps along the road. We are not there yet, but I think this is a good road to be on, because it kind of captures the essential things about what's going on. So the first thing we're going to do on this road of the human-robot collaborative POMDP is we're going to refactor our state. We're going to say that the state has two parts. It has the physical state of the world, where's the robot and where's all the objects that it might need to manipulate. And the second part is the human's mental state. What does the human want me to do? What are the human's goals? How are they trying to cause the world to change? And what does the human want the robot to do? So once we've done that, we can refactor our reward function to say that our goal is to make the person happy. So our goal is to figure out what the person wants. We don't get to observe it, but if we could figure it out, we could make plans in order to maximize our reward. So our reward is for making the person happy. So now, well, we don't know what the person wants. That's a latent variable that's out there in the world. What does the person want? How do we figure out what the person wants? Well, we can refactor our observations to say that there's physical observations from my physical sensors. There's language. And here I'm just going to assume somebody gave me speech recognition. Although, in general, I'd really like to go all the way to audio and get things like how loud am I talking and prosody and all that stuff. But for simplicity, we'll just say language. And gesture. And similarly, I'd like to go all the way to the sensors for that too. But anyway, for now, we'll just say that I'm running a gesture tracking thing, and it's doing something. I can observe it directly. And then by observing the language and the gesture, I can try to predict the human's mental state. So then I can kind of look at this factor in the model, the problem of observing the language, which is shaded, and predicting the human's mental state. And maybe I can assume I know the physical state for this subproblem. and then try to predict what the person wants by observing their language. A related problem is trying to choose actions that are sort of social actions that cause the human's mental state to change in particular ways. So I can choose to ask a question knowing that that will cause the person to understand that I don't know something, and on the next time step, they might give me another observation that gives me more information and lets me continue operating autonomously. So these two factors I call communication for collaboration. So the next thing we have to think about is sort of the physical actions in the physical world. So if we really want to be able to give these really abstract commands like clean up and really fine-grained commands like move forward a little bit, then I need some way of representing what the robot can do in the world so that the language can hook into that, so that I can specify goals at all of these different levels of abstraction in a way that kind of hooks into the language. So this is what I call action for collaboration, the ways that we represent what the robot can do. And then the final piece is perception for collaboration. This is like looking at my physical sensors. What do I think is going on out there in the physical world? And you might think that this is something that we can delegate to the perception people. But it turns out that there's a number of very interesting examples where you can see that perception and collaboration are integrally tied. So one of them I call the speck of dust problem. So I would like to be able to tell my robot, there's a speck of dust on the floor, and it's ugly, throw it away. And there's one on the stage. Fortunately for me, they didn't clean too well here. Here it is. Maybe you saw it drop. And before I said those words, I really hoped the robot wasn't tracking every speck of dust on the floor, because that would obviously be completely computationally intractable. But after I said those words, that speck of dust had better be among the most important things in that robot's life, because its goal is to do what the person wants, and that person wants that speck of dust gone. So somehow we need the language and the collaboration and the goals to hook into the perceptual system, essentially to act as some kind of attentional mechanism. And another example sort of related to this is the idea that I'd like to be able to say to the robot, get me my mug, it's in the cupboard that's full of stuff. So to determine if the cupboard is full of stuff, I have to actually make a plan and open the cupboard and then look inside and decide if it's full of stuff and then look for the mug. So a perceptual search problem, like find the mug, it's pretty easy to construct examples where I might need to access almost any other part of the robot system. I might need to have the full power of the robot's ability to like open the cupboard and look for the mug in order to solve these problems. So this is what I mean by perception for collaboration. So I'm talking a lot about a big generative model at a time in very deep days. So, of course, deep learning is a thing now, and I'll talk about some deep learning work in this talk. I think that if we want to connect language to our robots, we need some kind of underlying framework that describes what the robot's seeing and doing and sort of intuitively matches what the words are saying. We need something like this. And I see deep learning, or Ken likes to call it hyperparametric function approximation, as a particular discriminative approach. It's really discriminative, right? Lots of parameters for learning conditional factors in some underlying generative model. But to really make the next leap forward, I think you have to think about like what is the underlying generative model? What are its inputs? What are its outputs? What are its latent variables like? So that your deep net can match the structure, because it doesn't have to come up with this from nothing. There's things we know about how the world works. And I think in some cases it's better to learn them. In other cases, there's nothing wrong with telling the robot or encoding it in some way. So this is sort of the overarching framework that I'll be talking about. So the first thing I'm going to do is kind of give an example of how this plays out in order to do communication for collaboration in a relatively simple task, but it kind of captures this POMDP decision theoretic aspect. And then I'll show how we can do this on more complicated language, and we can handle a more complicated action space. And then I will just give a flavor of our work on perception, which has lots of cool videos, but I won't have time to go into how it all works. So to start out, we wanted to think about the sort of simplest possible problem that captured aspects of this POMDP decision theoretic nature. So we looked at the problem of object fetching or object delivery. So the idea is that the robot its job is to deliver objects to the person. And the human is going to use language and gesture in order to communicate which object that they want, and the robot has to figure it out. So for example, you might say, can I have that ball? And of course, in general, this would be like a mobile manipulator, but we're using our Baxter as a model. So you might say, can I have that bowl? And then you can imagine that we know the physical state, so there's a bunch of objects, and the human's mental state is which object do they want? And then we can have a multinomial belief state over that. So this is initialized to uniform, although you could imagine prior knowledge might inform this, but here we'll say it's uniform. And then it's not too hard to write down a generative keyword-based kind of model that does language and gesture in order to do a belief update that will enable it to interpret the answer, an updated belief state where if I say, can I have that bowl, and I point, there's two bowls in the scene, but the gesture disambiguates it. And it'll figure out that this is the object that it should hand over. And we had a paper a couple of years ago about doing this. It was the first thing to use language and gesture. There's a kind of cute generative model for gesture. But things get a little bit more difficult if you make the situation more challenging. So here, we're going to just move the person back and rearrange the objects a little bit. So he's going to point and say, can I have that marker? And here, there's now two markers in the scene, just like before, but the gesture is no longer disambiguating because the markers are close together and I'm far away. So it can't figure out what marker that it wants. And a lot of the existing work in robot language would just make its best guess and hand it over and get it wrong a lot of the time. But instead, what we did is kind of took this POMDP framework, this is like a really general one, and we made something that we called the fetch POMDP. It stands for feedback for collaborative handoff, where we made the state, the human's mental state, the human's desired item, and they also keep track of the last object that the robot pointed to. And then we have a keyword-based language model and a Gaussian pointing model. If you're doing gesture, it's not this vector, it's from your eyes to your finger to shoot out the ray to figure out what they're pointing at. And then using this model, the robot, and the reward is to infer the correct item. And using this model, the robot in this situation can figure out that the right thing to do is to ask a question. So it picks one of them and it says, this one. And the human says, no, not that one. And then the robot does an update, belief update, and figures out that the right one is marker number 2, based on this question and answer. So it asked a targeted question and got an answer. And what's cool about this framework is that in the unambiguous situation, where it knows it won't ask a question, but in the ambiguous situation, it'll automatically decide to ask a question. And it all happens very quickly and very fluidly. So I'll show you a video of what this looks like. We're supposed to.
Final answer. You wanted object.
Okay.
Can I have that bowl?
Final answer. You wanted object 4.
So here he's close, he points, and it almost immediately knows and responds and hands off the object. For speed, in our user study, we didn't actually pick up the object and deliver it.
Can I have the metal object over there?
This one.
No, the other spoon.
Final answer. You wanted object 6.
So here, in the ambiguous situation, it asks a question, it gets the information from the answer and disambiguates to hand off the correct object. And it's all happening really, really fast. The faster you can respond, the cooler the robot feels. That's one of my rules I tell my students. So we wanted to know how well this worked. We did a user study with 16 participants within subjects, so 54 trials times the 3 designs, so lots of different trials. And we had 3 different algorithms. We tried never asking a question, we tried always asking a question, and we tried using the fetch POMDP in order to intelligently ask a question. And we measured 2 objective metrics, the speed of the interaction and the accuracy of the interaction. And we had 2 different cases, the unambiguous case where we had them close, and we had different objects spread far apart. In the ambiguous case, where we move the person back, we put the object close together, and we arrange them so that there was more ambiguity to make it elicit these information gathering questions. And what we found as a result of our study is that intelligently asking questions is both faster and it's more accurate than the average of the baselines. So we thought that always asking a question might be slower, but it would be more accurate because you're getting more information than intelligently asking a question or never asking a question. But actually, always asking a question kind of confuses people because they kind of know when they've communicated enough. And if it asks a question when they're not expecting it, they don't always give us a good answer, or they get kind of confused about it, and that actually makes performance drop off. So in our accuracy in the green case here, in the ambiguous ones, you can see that the fetch, the POMDP approach, is more accurate than both never asking a question, which is not surprising, and the fixed policy of always asking a question. And then it's similar in speed, although there's a slight statistically significant improvement compared to always asking a question. So this is cool because we actually showed on real untrained users that this framework allows the robot to respond more quickly and more accurately to the requests. And additionally, we had this interesting result in the post-study questionnaire. This model was intentionally very simple, keyword-based language model. It didn't understand left and right, but 38% of our users thought that it did. And the reason we think is that it was so intuitive to have this question and answer that they would use left and right. It didn't understand, but the language and the gesture made up for it, and so it was able to respond successfully. They actually thought our robot was more capable than it actually was. And in my previous work before this, we kind of did more sophisticated language models, and I believe in more sophisticated language models. But for this, we wanted the simplest possible thing, so it was kind of a keyword-based approach. So we can kind of see, if we go back to our human-robot collaborative POMDP, this factor, this language factor, kind of breaks up. You can pretend this is a keyword-based language model, or you can even go back to our older work on GQ, where we had a compositional semantics kind of model, where it breaks up according to the compositional structure of language. And it allows the robot, by putting this together, to infer a human's mental state, to infer a belief distribution over the mental state, and then take information gathering actions. And you can also, we saw here very, very simple question asking actions in some of my previous work, not in a POMDP setting, but we showed that there's much more sophisticated language generation. So here the robot is assembling IKEA furniture, and it gets stuck. And you might imagine that it would say, "Help me." But without really watching what the robot's doing or knowing very much about the robot, it's hard to figure out from this scene what the robot wants. So you might imagine instead that you could say, "Please hand me the white table leg." But here in this scene, there's actually 3 white table legs. There's 1 on the table, and there's 2 on the floor next to that half-assembled table. And the one that the robot needs is the one that's on the table, because that's the one that it can't reach on its own. So what we'd like to do is intelligently generate requests for help that take into account this context and ask a targeted sentence that picks out the object the robot wants. And the details in the paper, I'm not going to go into it, but we showed that we could generate targeted requests by saying something like, "Hand me the white leg that's on the table," by essentially modeling how hard it is for the person to understand this request and detecting there's ambiguity, and then adding these extra things to it to make it answer. So this sort of says that in the communicative action space, there's also this compositional word-based, language-based structure that you can exploit in order to intelligently generate these requests for help. So the next thing I'm going to talk about is the problem of sort of expanding this. This was a very simple problem, expanding this to more of what the robot can do. So we'd like to put the metal crate on the truck, we'd like to do move backwards 10 feet, and we'd like to move everything from receiving to storage. So to do this, we somehow need to have a representation of the robot's actions that allows it to plug into everything that robot can do. And it's sort of, the sort of first thing you think of is some kind of hierarchical planning framework. So there's a lot of work on existing hierarchical planning. There's a lot of work on options, which are these closed-loop policies for taking action over a period of time. But the problem with options is twofold. First, there's a large branching factor. If you add options to your low-level actions, now you have twice as many actions, and you have an even larger space that you need to explore. And depending on what options you have, a lot of them might be not relevant to what you're trying to do right now. A second problem with options is they come with a policy. So if you have an option for opening a door in your lab, and then it's a policy, states to actions, and then you try to open a different door in a different place, it is difficult to make a generalizable, reusable option at the policy level. And a lot of the work in kind of grid world, like move to door, open to door options, they explicitly don't do that. So like there'll be an option for moving to door A and a totally separate option for moving to door B. And this means that it's hard to generalize to new states. And then HTNs, hierarchical task networks, are interesting, but they don't really work in non-deterministic situations. There's some work in non-determinism, but we really want something that takes the uncertainty about transitions and the uncertainty about perceptions seriously, so we can reason about that. And then there's some interesting work, MaxQ, where it divides the search space hierarchically over tasks, and they show that you can learn in this framework. But the problem with this is you need to search in the abstract space all the way down to the lowest level. And so you again get this combinatorial explosion if you really want your hierarchical space to contain all the possible actions that the robot can do. So a lot of the existing work in this area has this kind of generalizability, reusability assumption. And the way we'd like to talk about it, I call it the Groundhog Day assumptions. So this is a movie. It's an American cult classic. I think a lot of you may have seen it, but if you haven't, it's really good, but slightly repetitive. And the premise is that Bill Murray plays this weatherman, and he goes to Puxatawney, Pennsylvania, to report on Groundhog Day. And he has a terrible day doing his reporting. And he wakes up the next morning, but somehow it's the same day again. The same song is playing on the radio, and then the radio announcers have the same conversation, and the same things happen every day. He gets to choose different actions, but everybody else is kind of reacting. They don't realize the day is repeating. They're living it through the first time every single time. But he gets to reset to the exact same initial state over and over and over again. And what this causes him to do is learn some kind of strange things. So here's an example of him robbing a bank. I'll show you a little GIF from it. So what happens is every day at about 2 o'clock, this lady comes and asks for quarters from the bank guards, and they drop the quarters. There's an accident. Every day at 2:15 that happens. And he's learned that this accident happens at the same time in the same way every day. And he kind of waits across the street for it to happen. He sees them bending over. He walks to the truck. He picks up the money bag and robs the bank. So he's learned a policy for robbing the bank, and it works. Here he is. But it's not the kind of thing that you might try tomorrow, because it's hard to plan on somebody dropping the quarters at a particular time. In real life, every day is a new day. So it's not the case that we get to reset to the same initial state over and over and over again. Instead, we're kind of sampling from a family of starting states. And then we're given a natural language command, which somehow specifies my goal. And then I'd like to immediately, in this state that I've never seen before, and in this reward function I've potentially never seen before, find a policy, solve this MDP or POMDP, and find a policy to follow these natural language commands. So in order to do this, we've developed a framework for hierarchical abstraction in MDPs, and we're now thinking about how to do this in POMDPs. We call it abstract Markov decision processes. So an AMDP is a hierarchy of MDPs. An action in the abstract MDP defines a reward function in the lower level MDP. And if you happen to have a policy that satisfies that reward function, you're back in options, and that's great. If options are the right thing, you can use them. You don't have to solve it. But if you don't have a policy, then you can run planning, in order to find a policy that satisfies the reward function. And it's a lot easier to generate policies, generalizable reward functions, than it is to generate generalizable policies where every single state has to have an action. And then there's a state abstraction function that maps from child states to abstract states. And we'll give it an abstract transition function. So we can do complete planning at the high level, and then that maps to abstract reward functions one level down, which I can then solve, and then kind of go all the way down to concrete things. So for example, this is one of our toy problems. It's a mobile manipulator robot in a grid world. We call it cleanup world. And we have a 3-level hierarchy where the L0 actions are kind of the grid actions, north, south, east, and west. The L1 actions know about objects and rooms and doors. So you can move to a door, and then you can move to the room and to the object. And then the L2 actions only know about how to move objects in between different rooms. And when we run this on our actual robot, our L0 goes all the way down to the controllers that are running at about 20 hertz, moving the robot around, and then the L1 is the grid world. So this can go all the way down. I want to go all the way down to the PID controllers, and then all the way up to these really abstract actions. So by giving yourself this hierarchical abstraction with the transition function at each level, you shorten your branching factor instead of having it all in a flat space like in an options. By using reward functions instead of policies, you can generalize more in a new environment. And critically, you can have sub-problem specific algorithms at each level. So going back to the cleanup problem, if I'm supposed to move the red chair to the blue room, a nice path planning algorithm in this setting is A star, right? But the problem is if I'm moving the robot to move the red chair to the blue room. But the problem is my Euclidean distance heuristic. I want to minimize each action that minimizes my distance to the goal that makes A star work. For the first half of this, I have to move away from the blue room, and my heuristic isn't helping me. And then once I get the chair, I have to go back. If you add hierarchical abstraction the right way with AMDPs, then you get a sub-goal of getting yourself to the chair, and then your A star heuristic works. It's great. And then you get the chair, and then you move back to the blue room, and your A star heuristic works again. So you get this algorithmic level speed up in terms of planning by using a subproblem specific algorithm. This is just one example. We think a lot of, idea is we don't want to reinvent robotics. Motion planning is a thing, it's a good thing. There's a lot of good things that have been figured out. SLAM is a good thing, and we don't want to reinvent all that stuff. And I don't really think we need to learn all of it. We want to be able to just fit it in our framework and use it and talk about it. So this is showing what it's like on a real robot. So this is our TurtleBot in a fully observable setting. So we're using a motion capture system to track the objects. And its goal is to have the orange block in the blue room. And what the idea is, by using MDPs, you can mess with the robot. You can move that block out of the way, and it will automatically and very quickly find a new policy, sort of react to this change in the environment. It had to go in the room to turn around and then come out, and it figured that on its own in order to move this block into the room. And this is the advantage of using a decision theoretic framework, a policy and not a plan. And I know I said reward functions, but we have reward functions that you solve to find a policy to get this behavior. So now, using this framework for hierarchical abstraction, we can revisit the question of language abstraction. So still thinking about this toy mobile manipulation domain, we'd like to be able to understand really fine-grained commands like go down 5, right 5, 1, up, right 4, down 1, left 1, and up 3. In practice, probably the human would usually say shorter ones, like move back a little bit. And then we'd also like to understand more abstract commands, like take the red chair to the blue room. If you only had low-level instructions, then it might be you could live with it in a grid world, but if you looked at a larger environment, this is a schematic of the ISS, it's going to get old really fast, saying go down 1, up 5, 6. You just don't want to do that. And if you only have high-level instructions, you use granularity. So the time when you want the robot to get out of your way and the only thing you can say is clean up the room, it's not good. You need to be able to say these fine-grained things too. So what we did is we sort of built on prior work where we we make the simplifying assumption that the human's mental state is essentially one and the same in the reward function. This is not a POMDP setting, this is an MDP setting here. And we're going to estimate the probability of the reward function given the natural language command. And the previous state of the art was IBM Model 2 language model with an arbitrary planner at RSS a couple years ago. And in our paper this summer, now we're deep, yay, deep learning. We replaced the IBM Model 2 language model with recurrent neural networks. We tried a couple different deep models, which you can read about in the paper. And we replaced the arbitrary planner with an AMDP planner. And the probability, instead of before we were learning a reward function given the command, here we're going to add a new latent variable, which is which level of abstraction are you at, as well as this reward function, which is defined in a symbolic language of reward functions. So going back to the human-robot collaborative POMDP, what this is saying is that the action space is hierarchical. And more than that, I'm proposing a specific hierarchical framework that can capture some of these different language commands at different levels of abstraction. And my goal in one of my litmus tests for the framework is that things like a star and motion planning should just fit in the framework. If there's a really good domain-specific algorithm, I shouldn't have to reinvent it, I shouldn't have to learn it, and I shouldn't have to use a general-purpose inference algorithm to try to do what a star is doing. So I want it to just fit into the framework so I can use it and then talk about it, talk to the robot about it. So in order to ask how well this worked, we did a data collection where we showed annotators videos of the robot, and we used this cleanup world domain. And then we asked them to generate natural language commands at different levels of abstraction. We explicitly told them the levels of abstraction and told them to do commands. And this is the example. These are just commands from the data set. This is not associated with the video. So the L0 was like really fine-grained, go 3 down, 4 over, 2 up. The L1 was rooms and doors, go to the door, enter the red room, push chair to green room door. And L2 was go to the green room or bring the chair to the blue room. And we tried a couple different deep models. I'm just going to show the IBM 2 versus our best deep model, which was a recurrent neural network that jointly did level selection as well as reward function prediction. And it works pretty well. We get about 80% at inferring the correct reward function. And using the AMDP framework, of course, is better than the generative model. Not a surprise there. And using the AMDP framework, our planning time is also much faster. And this was in simulation, but what those numbers down there mean is that the robot responds much more quickly. When you say a command, the robot's going to start moving much more quickly. And there's a lot of variance in that. Well, there's not a variance in the median. But anyway, there was, on the more complicated commands, it's much, much faster to use AMDPs to plan. On the simpler environments, AMDPs actually impose a little bit of overhead on really simple environments. But it really, really saves you time in the complicated environments. So here's what it looks like.
Take the block to the green room.
So anyway, take the block to the green room. So we infer the level of abstraction, and then we infer a predicate goal-based kind of reward function. We solve the resulting MDP. We find a policy. So all the stuff where we move the block out of the way and stuff, it would keep trying to move the block, just like you saw in the AMDP video.
Go to the red room.
So here's giving a high-level task, go to the red room. And then we command the same thing
Go south, south, south.
in low level. And it infers the first one was a high level. I'm just going to do it. The other one was low level, and I'm going to find a lower level command. There it goes. So coming back to the human robot collaborative POMDP, this is how I think about hierarchical abstraction and how hierarchical abstraction can enable efficient learning and inference, well, mostly inference in this world, although I think learning too. I believe learning too, although we haven't really done it yet. And it can enable natural language, understanding natural language commands at these different levels of abstraction. And going forward, what I really want to do is kind of combine these two pieces, so where we have a human mental state representation that's not just what object do I want, but what goal do I have in a symbolic language about what the what they want the world to be like, and then infer uncertainty over that, and then ask targeted questions within this kind of framework, this hierarchical framework, in order to collect information and manage uncertainty and really get to something like a collaborative planning dialogue where you kind of agree on a common plan and you go off and do it. So the final thing I want to talk about is perception for collaboration. So this is the factor of trying to estimate the physical state of the world given the sensor observations. And I was really motivated to start to work on this by becoming frustrated with the extensive use of fiducial systems in robotics. And then, you saw that in my work, in this talk, I'm using them. So, but a lot of people use them, and they use them because they're more reliable and they're easier to get working than something that uses vision or point clouds or something like that. But the problem is, if you imagine a more complicated environment like my lab or your lab, or this is the International Space Station, it's really not practical to envision putting fiducials on all that stuff. Additionally, we really wanted the ability to do precise manipulation. So this is a 1/4-inch nut and a bolt. And we'd like the robot to be able to put the nut on the bolt. I'd like to be able to say that, and I'd like it to be able to do it. But to cause this to happen, I've got to be accurate in my positioning down to the millimeter in order to get the nut on the bolt and to get it to engage. So I was talking to Rob Platt. I emailed Rob and Ken this morning, and I said, what's the state of the art in sort of open object manipulation in clutter? And the number I've been using is about 90%. I think you said 98% now. No, that was the vacuum clipper, right? So like it was more, I'm going to say more or less 90% at picking up objects in clutter. So this is my mom and my dad's dishwasher at home, ready to be emptied. And if you were trying to empty this dishwasher and you're at about 90% accuracy, having not seen these objects before, that means you're going to miss 3 or 4 objects maybe, and not every miss is going to result in a broken dish, but every miss is definitely a chance at a broken dish. And it doesn't take too many broken dishes before that robot is gone. Similarly, on a factory line, 90% is nowhere near good enough for that robot to be useful on the line. We need lots more zeros, lots more nines, 99.999 or something like that. Also, this dishwasher has a lot of glasses. So here's some shiny, transparent things. They're everywhere in the world, and we'd really like to be able to manipulate those objects, and it's hard. And even we'd like to be able to do them in scenes like this one. So we brought a sink to our Baxter. We filled it with water. We put a pump in there to turbulate the water because we didn't have plumbing. So this would be like the water's running in the sink. And you'd like to be able to pick up the fork out of the sink and do something with it. Put it in the dishwasher or put it in the dish rack. And this is hard because this is what the Baxter wrist camera sees. You see the fork. It's shiny. And it reflects the overhead lights. And so does the surface of the water. Also reflects the lights. And it's really hard to distinguish between the two reflections. There's like the same thing that you're seeing in these two different places. So it's hard to figure out where the fork is precisely enough to pick it up. So I won't go into all the technical details, but our goal to solve this problem, what we did is came up with a framework. We didn't really invent this framework. Graphics people use it all the time, but not for perception. But this framework exploits the robot's ability to move its camera. So instead of just using one camera view, we're going to move our camera around. Baxter has a 7-degree of freedom arm, so we can move it in very creative ways, and exploit the ability to image each point on the object from many different viewing angles. And there's many ways to exploit this. This is basically allowing us to capture the light field by moving the camera. It's time-lapse light field, but you can also imagine arrays. Hanu at Northeastern is working on an array for capturing this. The thing that's different is the wide aperture. So we're doing synthetic aperture photography, but by moving our camera by this distance, we can generate images as if through a synthetic 35-centimeter lens. Not something you really want to carry around with your mobile manipulator, but if you move your camera, you can generate these images. And we have a probabilistic framework that kind of talks about this that I don't have time to go into. I call it probabilistic object maps, and it takes into account the light field to be a generative model that goes from pixels to synthetic photographs to objects, poses, and appearance models. And we can kind of say there's a lot more to it than this, but anyway, at least there's objects going on here. The physical state factors in terms of objects. And I want to be able to reason about how those objects change over time. So Ken Goldberg visited Brown a little while ago, and he showed this video of a child building a stack of blocks, and he made the claim that a robot couldn't do this. He meant picking and clutter, although there's not that much clutter in this video. They're kind of well-separated blocks. And we made a bet with him that we could do it. So we bet $100 that our robot could make a stack of blocks, not just one stack of blocks, because I really wanted to emphasize the robustness. So we said not only could we do it once, we could make a stack 8 blocks high, which is in this stack. We could do it 10 times in a row. And a couple days later, we kind of called him on his bet, and we sent him this video of the robot building a stack of blocks using this light field stuff to localize the blocks with a monocular camera. So this is a monocular camera that moves, localizing the blocks, then doing an open loop pick and place in order to make an 8-block tower. And I won't play all 10 trials, but that's 80 successful picks and places in a row in one continuous take in order to show that we kind of have this capability to do the tower. Here we go. The whole video is online if you want to see. And Ken sent us a check. Thank you, Ken. We can also use this to do very precise localization. So if you know Baxter, its ability to move itself is a couple of millimeters. So we can use a monocular camera to localize the nut and the bolt using this synthetic photography stuff. This is a regular monocular camera. Localize the nut, which is shiny, and the bolt using vision, and then do an open loop pick and place in order to screw the nut on the bolt. We're able to localize objects as precisely as we can move our arm, which is kind of the limit of what you need, because if you can't see more than you can move. And then you can look at these shiny reflective objects. If we only use one camera image, on the green fork, which is not shiny or reflective, we do it perfectly, 10 out of 10. But on these other objects, we miss them a lot. But if we change to using about 140 camera images collected from multiple viewing angles, our shiny metal fork goes to the same as the not shiny fork, and we have respectable performance on all of these other objects as well. And we can also go back to our sink in the water. This is what the robot sees. This is our synthetic photograph that the robot generates of the scene. And this is working because of image averaging. Some people ask, how is this different from image averaging? It's not. It's a kind of image averaging. It's just the right kind of image averaging to do when you have multiple viewing angles. And that allows you to kind of see through the water and focus on the fork. So the fork pops right out, and you can use image matching to localize it and pick it 24 out of 25 times. So what's amazing about this is that something really stupid like image matching, this is all image matching more or less, works so well. You're free, of course, to run a deep learning thing on top of this synthetic photography stuff. And you can, if you think if image matching works so well, something deep might work better or might generalize more. The other way I think about it is if you sort of imagine a convolutional network, running a sliding window over an image, mostly that's done today in the image space, right? The plane of the image, the pixels of the image. But by using synthetic photography, I'll go back to this picture, I can choose to put the image wherever I want. So if I'm doing picking from a flat surface, then I can say, make a synthetic photograph where the image plane is basically the bottom of the sink. And then when I'm running my convolution, it's literally convolving over the surface of the sink, without any camera angle stuff. It's all gone because I decided I want a view on the surface of the sink. And so we're really excited about the potential of applying those sorts of techniques to this sort of synthetic photography data, although we haven't done it yet. I hope some of you do it. All right. So this is sort of talking about perception for collaboration, to perceive transparent and reflective objects, to automatically acquire object models in order to robustly detect, localize, and manipulate objects, and do cool things with non-Lambertian, shiny and reflective objects in non-Lambertian scenes, like a sink filled with water. Okay, so going forward, I sort of talked about communication for collaboration, action for collaboration, perception for collaboration. We started out with this generic POMDP, and we saw that it's a lot more complicated. And I think there's a long way to go. I don't think this is the whole story, but this is the road that I'm on. So thank you very much for your time, and I look forward to questions.
Great. We have time for a couple questions.
Hi, awesome talk.
Thanks.
The abstract MDP framework seems to be a really good way to compute decision-making policies. Do you think it would be possible to run that backwards? So, like, given demonstrations of a few tasks and like sequences of actions, do you think you can infer the decomposition?
Yeah. So mostly we've done hard coding the AMDP hierarchy. We're very interested in ways of learning it. And you can sort of imagine an IRL kind of framework. I want to learn the reward function. You can also imagine generalizing this. If I have a bunch of options, I want to generalize that to find an abstract policy. And I'm very happy to have demonstrations. So we actually have an active virtual reality and augmented reality project going on in my group that I didn't have time to talk about. But we are very interested in using the VR, which is a very powerful way to teleoperate the robot by a person, to provide demonstrations of the robot doing complex tasks, and then seeing if we can challenge our learning people to and also all of you, to kind of go back and learn from that data. The thing, Sonia mentioned the Million Object Challenge, and we have this Baxter thing to kind of learn about objects. But the problem is that our learning right now is, the way I think of it is kind of additive. Like, we'll learn about an object, and then we'll learn about another object, and I can add that, and then another one, and I can add that. But I really want, before I hit go and make all of you use your Baxters to do this, I want the learning to be multiplicative. So I learn about an object, and then I multiply that knowledge by some other object, and I get something about objects in general so that I can handle unknown objects that I haven't seen before. Does that make sense? Okay.
I was wondering, in the first part of the talk, you were showing asking questions that clarify which object.
Yeah.
Have you tried learning actions to clarify, to reduce the uncertainty? So basically, can I move this thing? Can the robot automatically learn to move these things away because the principle is that if the objects are well separated, then and so on?
Yeah. So Ken complained about my block stacking video because we separated the blocks. And we imagined, we didn't shoot this, so I don't have video proof of this, but we think what we could do is program the robot to pick up some blocks and drop them on the table and stir them around, find the well-separated one, and then do what we were doing. But that's not really what you want. You really want the ability to infer those sorts of actions. So where I want to go is, I don't know if I should say this acronym because it's terrible, but I think I'll say it. It's called APO-UMDPs. Abstract, partially observable, object-oriented Markov decision processes. Okay? I think you need them all. I think that's what this is. And in such a framework, I think if you have efficient learning and inference, what I want in the right framework, I think SLAM, I don't want to reinvent SLAM. I want to, look at here Durant White's review paper and put it in level 3, let's say, of the APO-UMDP for mobile robots. Similarly, I think that there's, I kind of skipped over this, but there's a kind of Bayes filtering approach to object reasoning where there's objects and they have poses and they have appearance models, and of course, more generally, they have affordances, actions, articulations. And there's sort of a bunch of hidden objects, and I get to do a control input, but that's really my action space. And then what's off over here is the idea that there's a transition model and an appearance model for the specific object you've got, but then there's also a category-based version of that. So if I know that you have a mug, then I can have a prior or something on what mugs kind of look like and that there's a handle, and if I can find the handle, that might be a good place to grab it. So I kind of imagine something like that, if plugged in the right way, with a lot of hand-waving at this point, would enable the behavior that you talk. At least it seems like it's got some of the elements in order to do that.
I really loved all of the videos you had and all of the hardware that you guys have taken your models and applied it to. Something that I wonder about is you're doing on the videos, it's like a 20x or a 60x speed up, and
Yeah.
what do we need in order to get robots up to speed?
What do we need in order to get robots up to speed? Yeah, so a lot of the reason the videos at the end were sped up was because we're doing it over and over and over. So when we're doing the block stacking, you know, I want to show 80 pics, and I don't want you to wait. And, you know, maybe I could have sped it up more, but you can't even see it. The other reason our light field stuff is slow is because we don't yet have a camera array, and we also don't yet reason about what data we need to collect, so we just collect it all, and that takes a long time. Now that we know that it works when you collect it all, another natural thing is to collect less of it. I think a third reason our robots go slow is sort of boring, but it's because a lot of the work that we do, you know, when you actually, a lot of it's in simulation, and when you have somebody sit next to the robot and make the robot do something, that's happening at the end when you're making the video. And it takes more time to make it fast than to make it slow. If it's slow, you can kind of, you know, watch what happens and stop it if you need to kill it, and you have to, like, you know, go through and optimize all that stuff. And I think a lot of making it fast is kind of sitting next to the robot for a week instead of a day when you're making that video in order to make it go faster. There is some very interesting work, like in Nick Roy's group. Charlie Richter did a thesis with a race car that's going screaming through this data center very quickly using a deep learning algorithm for predicting the policies. I also think it's really okay if it's slow, because the first thing is just to get the robot to do it. You know, once it can do it and do it reliably, then we can always make it faster. And I don't think it's just engineering, but I think a lot of the reasons it's slow are like relatively easy things to fix that take time, and we just don't have enough time because we want to go to the next new thing instead of making the old thing faster.
All right, and on that note, let's please thank our speaker once again.
Thank you.